So today we will talk about deep learning computation for economic theory and its applications to distributed computing. So my name is Jung Kim. I'm with Korea University School of Electrical Engineering. So this work is by my sons at Korea University, Myungjae Shin, Suyeon Park, Young-eun Kang, and Dong-eun Kim. And then we have external collaborators. Those are my collaborator at Computer Science UC Irvine and Professor Min Seok-chae at Jeju National University. And then this work is under the project support that's called Hanyang ATRC. And the central name is 5G Unmanned Vehicle Research Center. So today we're gonna present the research results by this effort or support. First of all, I would like to let you know why we need economic theory and what is the distributed optimization here. So as you can see in the left-hand side, if you want to solve any kinds of problem in real world, you are making optimization formulation. So we have linear programming here, but it can be convex programming as well, and we can get into optimal solution. So in order to design linear programming or convex programming, you have to know all the information in your variables or constraints. However, in general, so understanding or getting all the information about these kinds of constraints is very hard and it's very huge burden. That's why in order to make any kinds of optimal decision, you have to make a decision under certain amount of uncertainty. That's why now we're going to discuss about your decision making under uncertainty. For this formulation, usually we are using microeconomic theory. So we usually use game theory, stable merit theory, or auction theory. So we're gonna study about that one by one very briefly today. First of all, let me introduce what is the game theory. Game theory is the thing what we can make a decision under uncertainty. So suppose that we have two players, KBS and MBC and KBS. So this is called payoff matrix in game theory. So this is payoff matrix by MBC and KBS. So this is kinds of the competition to get more people in the program. So KBS, MBC, those are very famous broadcasting company in South Korea. So MBC may play movie, opera, or comedy. KBS may play movie, opera, or comedy. And in the case, suppose that both of them are playing movie. So in the case, MBC will take 35% of the people, and KBS will take 65% of the people. So this is the point when they make a decision as movies and movies. But our problem is that we want them to be strategic. So suppose that we want to make sure that both of them are very intelligent. So in this case, suppose that MBC plays movie and you're gonna take 35% or 15% and 6%. We don't know which one is better. So because the reason is that MBC does not know what KBS will do. So if suppose that KBS is playing opera, so in the case, MBC exactly knows that it's gonna take 50% here, 58% here, 14% here. That's why MBC will play opera for sure. It's very easy. But the problem is that MBC does not know what KBS will do. So then what they have to do. So suppose that you are an MBC. Then if MBC plays movie, then it's gonna take 35%, 15%, or 6%. Then we can say that this decision for movie can guarantee at least 15%. Okay, but in the same way, suppose that MBC plays opera, so in that case, it's gonna guarantee 45, 58, and 50. So then we can say that it can guarantee at least 45%. It is minimum. But lastly, suppose that MBC is playing with comedy, then it's gonna take 38%, 14%, and 7%. Then it means that it's gonna guarantee at least 14%. So among these given three, so you have to pick the maximum, so 45%. So that is opera. This is the MBC's optimal solution. In the same way, KBS has three options. For the first option, movie, it can take 65%, 55%, or 60%. That's why this decision will guarantee at least 55%. And suppose the MBC plays opera, then it's going to guarantee at least 42%. When KBS plays comedy, then it's going to guarantee at least 30%. Among these given three, 55, 42, and 30, and then we can say that this can take the maximum result. That's why MBC will play opera, KBS will play movie, and this point is their optimal solution and Nash equilibrium. Okay, so this point is Nash equilibrium for both of them. So next, economic theory is stable marriage. So in stable marriage, so this is those are very famous actors in South Korea, and his wife is here. His wife is, so I make a note here. He's A, she's A as well. So he's B, then his wife is here B. And if they are in the same table and they are in the same table, and it's not stable because his first preference will be her, and she will be the second preference for him. But in his case, his first preference will be here, and this is the second priority. That's why both of them are with their second priority. That's why this matching is not stable. So in order to make a stable the system, we are using the stable marriage theory. Okay, so we're gonna look at this one more details in next slide. So suppose that you want to make two movies. In order to make two movies, you have to recruit actors. So you are recruiting two actors, Kim and Lee, here as a man, and as a women, you are recruiting John and Jin. So this is the set of the actors make two movies. So in order to make two movies, you need two pairs. Okay, then for these four actors, you have to let them make a preference list. This is the preference list of the Kim. This is the preference list of the Lee. This is the preference list of John. This is the preference list of the Jin. So in that case, Kim's first priority is John, second priority is Jin. Lee's first priority is Jin, and second priority is John. John's first priority is Kim, and second priority is Lee. Jin's first priority is Kim as well, and second priority is Lee. So in this case, you can make these kinds of two combinations. Okay, then we have to check whether both of them are stable or not. So when you look at Kim, and Kim's partner is John, then you have to look at the preference list. As you can see here, Kim's first priority is John. That's why it's fine. So this is fine, and he's okay with this decision. Then you have to look at John's decision. So John's first priority is Kim. That's why she's also okay with this matching. So this is also fine. So let's look at Lee's preference list. Lee's first priority is John. That's why this is okay as well for him. So let's look at the preference list of the Jin. Jin's first priority is Kim. That's why she is not satisfying with these kinds of matching. That's why Jin will ask to Kim whether please be together, but he will deny because his first priority is John. That's why this is stable because she cannot move to this one or she cannot be with the other partner. That's why this system is stable. Okay. So the point here is that in stable marriage theory, we cannot make everyone be satisfied with this kinds of system. Some people may not satisfy with the decision, but if the system is stable, that's fine. Sorry. So let's look at the next list. So let's look at Lee. Lee's first priority is Jin, as you can see here, but she's not his first priority. That's why Lee will ask to Jin that please be together, but Jin will deny because Jin's first priority is Kim, and she is now with her first priority. That's why she'll deny. So he has to be here. And John, let's look at John. John's first priority is Kim, but he's not Kim. That's why she will ask to Kim to be together. And Kim's first priority is John. That's why he will accept the invitation. That's why they'll be together. They'll go to stable status. That's why in game theory, in these kinds of the stable marriage theory, all kinds of unstable matching will convert to stable situation. That's why this is the theory which can make the system be stable. Okay. So this kinds of stable marriage mechanism is developed by Gale and Shapley. Those are very famous game theory economists, and both of them maybe Shapley got Nobel Prize in economics. He got a lot of prize from computer science theory. So this is called Gale-Shapley algorithm. Okay, this is So this we're gonna make a procedure to make a stable marriage in a faster manner. So suppose that we have 4 players here, and they have their own first priority, a preference list. So let's look at how they works. So A is with 1. So we're gonna make a stable situation by pairing both of them. 4 by 4 pairing. We're gonna make this one. Okay. So A want to be 1. That's why A is with 1. B wants to be 2. That's why B is here. C wants to be with 3. That's why C is with 3. And D wants to be with 3. That's why we have overlap here. So in this case, we have to ask 2, 3. So when we look at the 3, and C is here, D is here. Okay. So C is has the last priority. That's why D is better. That's why 3 wants to be with D. So that's why 3 wants to be with D. So C has to find another partner, another pair. That's why he has to look at the next one. But 2 is already with B. That's why we have to ask to 2. Which one is better between B and C? So B is here and C is here. That's why 2 will be with C. 2 will be with C. And this 2 is not here anymore. That's why B will be with 1 here. So when you but 1 is already with A, that's why we have to look at the preference of the 1. So you have to compare between A and B, but B is the last priority, A is the first priority. That's why this is not here anymore. So B has to look at the next one, 4. But 4 is not matched with the other guys. That's why 4 will be with B. And we have perfect matching here. That's why we are stopping here, right? So the beauty of GSA algorithm is that we can converge the solution quickly, as well as we have solution for sure. We have stable matching for sure here, based on GSA algorithm. So why GSA algorithm? But GSA algorithm is widely used in many applications. Among them, we're gonna look at the application in distributed system or computing systems. So this is router. So suppose that in this router, we have head of line blocking problem. So here we have a lot of packet those wants to go to this red direction. And in that case, 3 of them wants to be this way. But here, black one and green one, those are idle, but they cannot these packets cannot processed by this output because they are all blocked by red packets. So this is called head of line blocking problem. In order to solve this one, we are making virtual queues here. So even though we have only one input here, we can classify the inputs into 3 parts. So the first one is for red, the next one is for black, the last one is for green. So we have this classification, and then red will be here, will be processed here. Black one is not blocked anymore. That's why black can be processed here. Green can be processed here. That's why this can solve the head of line blocking problem. But in this case, we have to conduct matching every single time. So in order to solve this problem with stable marriage theory, we have to make a preference list for these outputs, for these inputs. Suppose that inputs are 1, 2, 3, outputs are A, B, C. So in that case, we have 2 packets for A here, 1 packet for B here. In 2, we have 1 packet in B. In C, we have 1 packet for A, 2 packets for B, 3 packets for C. So in this case, we have to make a preference list for input and output, and then we can conduct GSA algorithm, and that's it. So here, as you can see here, 1 wants to process A at first because we have more and more packets. That's why we want to avoid overflow. That's why in terms of A1, A has the first priority because we have to process A's packet very quickly, and then B and C, and B and C. In 2, B has the highest priority here, but we have no priority for A and C. That's why randomly we will gonna print out A and C. In C, C has the highest priority, and then B, and then C. That's why we have C, B, A for 3. So let's make a preference list for A, B, and C. So in this case, in the viewpoint of A, it takes 1 has the highest priority because it has 2 A packets. It has 0 A packet. It has only 1 A packet. That's why in terms of A, it has to serve 1 at first, and 3 and 2. That's why it has 1, 3, 2. In terms of B, it has only 1 packet here, it has only 1 packet here, it has 2 packets here. That's why 3 has the highest priority, and 1 and 2 are randomly placed in here. In terms of C, it has 0 packets here, it has 0 packets here, it has 3 packets here. That's why 3 has the highest priority, and A and B are located here randomly. That's why we can make this kind of preference list for the matching, and we can convert GSA algorithm, and we can get the solution quickly based on the algorithm. So this is the routing matching mechanism in internet system. Last economic theory, we're gonna look at the auction theory, okay? So in here, we want to show very simple example for the auction theory. So in order to buy this one, suppose that we have 3 we have 3 bidders. So the bidding from A is $10, this is $8, this is $6. Then this guy will take this picture. He's gonna be a winner because it pays a lot. It pays maximum value for this product. So it says that he can pay $10, then this auctioneer or seller will get $10. That is called revenue. So you're gonna get $10, and this product will belongs to A. But in this case, we have the concept of the utility. Utility is the bid minus payment. Their bids are 10.86. That's why they have 10.86. And A's actual payment was $10. That's why it is $10. And since B and C did not get this product, that's why they did not pay anything. That's why the payment will be 0 and 0. That's why this becomes 0, this becomes 8, this becomes 6. This is called the first price auction, okay? But let's look at the second price auction, okay? So in second price auction, so suppose that we have only 1 product, and then they are bidding all together. So A wants to pay $10, B wants to pay $8, C wants to pay $6. So in this case, A's bidder is the maximum. That's why A becomes winner. But the payment is not $10. The payment will be the second price, $8. That's why auctioneer seller will take $8. This is called the second price auction. Okay, so here in this case, the utilities are as follows. The bid values are 10.86. That's why we have 10.86. And A actually paid $8. That's why their payment is $8. And finally, the utility is 2. But why we are using second price auction? The reason is that second price auction is truthful. So the reason is that suppose that we have one fake malicious user. So it has fake bid $100 here. So in this case, he will gonna take this picture. That's why he can be a winner. And their payment will be the second price. That's why this becomes second price. Then when you calculate the utility for everything, so A's bidding is 10, but A cannot get this picture. That's why their payment is 0. In terms of B's actual value is 8, and he has to pay $10. And it means that it's gonna take the negative utility. That's why this kind of behavior will not happen in real world. That's why when we are using second price auction, we can initially eliminate these kinds of malicious users before starting the auction. That's why this mechanism is truthful, what we said here. That's why in order to make a truthful system, then we have to use a second price auction. But in terms of auctioneer, when we consider first price auction, he can get $10. For second price auction, he can only get $8. That's why in order to maximize auctioneer's profit, then this is better, okay? Then here, what I want to say is that when you are doing first price auction, it is good in terms of revenue optimal. You can take on $10, but it's not truthful. When you are using second price auction, it is truthful. That's why it's good. However, it's not optimal because it only gets $8. So our main purpose is that the system should be truthful as well as the auctioneer should earn $10. That's why we want to satisfy both of them. That's why we want to use we want to design optimal auction. So optimal auction should be truthful as well as revenue optimal. Okay.
So in order to design optimal auction, we usually using virtual valuation. This is called Mears auction here. So here, suppose the two users are bidding. Their bid values are B sub 2 and B sub 1. So suppose that this is $8, this is $10. So in this case, when we are doing the bidding, then this will get the product because the price is higher. But the payment will be the second price. That's why you're gonna pay $8. Okay. But our maximum was 10 in terms of the revenue in auctioneer. That's why we want to make this one nearby 10. But in order to this mechanism, in order to design that mechanism, so we have two virtual valuation function. So this one is mapped with pi sub 2. That's why this is the result about that. This b sub 1 has also its own pi sub 1 function. That's why it has this kinds of virtual valuation result. So we will compare not with this one for this one. And this is higher. That's why number 1 will be the winner. And the payment is the second price, this one. But this is not an actual payment value. That's why we have to derive actual value based on this one. So now we have this one, but one has its own function. That's why in order to calculate real value, we have to use the inverse function. But number 1 knows its own function. That's why we have to apply the inverse of the set sub 1. That's why here, this is our payment, Q sub 1. Suppose that this is 9.5. This is 10, 9.5. Now it has to pay $9.5. But this is nearby 10. That's why we can increase the benefit of the auctioneer or seller. That's why this is a better solution. So this kinds of mechanism is called virtual valuation. So from now on, we want to make a mathematical framework which can calculate these kinds of equation. That's why we are using the deep learning procedure here. So up to now, we studied about 3 major economic theory for make a decision on the uncertainty. In game theory, we have to make a decision when we do not know exactly what the opposite side will do. In stable marriage, we have to make a matching, but in the case everybody cannot satisfy fully. But at least we can make a system stable. That is for stable marriage. Lastly, we can get the resource, or we can compare the resource for taking that resource. That's called the resource allocation. So every multiple users wants to do the resource allocation on the truthful operation. Then we can use auction. Okay. So in order to make a decision on the uncertainty, then we are using these kinds of the economic theory, and this is called distributed optimization because we are making decision on the uncertainty. So now we're gonna see how deep learning can be used for these kinds of the economic theory, especially for auction theory. So as I told you before, in order to calculate the auction's payment, suppose that this is the second winner's bidding value. This is the function of second bidder's valuation function. This is winner's function and its inverse form. Then we can calculate our virtualized or our near optimal payment value. So this is the equation what we have. So this is the equation what we have here, right? So in that case, suppose that we have n number of bidders, n number of users are comparing, and by using ReLU function, we can eliminate the bidding which has less than 0 value. And then based on that, we will apply set of functions for individual bidders. Then we are using this one, and then we're gonna classify the result into G over 0, P over 0. G over 0 is for selecting the winner. So this is for selecting the winner, and this is for determining the winner's payment. So this one is for the payment, okay? So in this case, you can see the inverse function here. That's why it has inverse function as well, okay? So in order to select the winner, we have to select the bidder which is bidding the maximum value. That's why we are using softmax function here. So in this case, we just take the value which is the positive. That's why we just use the ReLU function. Now we have to look at how zeta function is designed, and that is designed with a monotonic network. So when you look at the monotonic network, we have some samplings over here. So when we get some values, we will add randomly more and more values. That's why we have weight value. Those are all positive. So we're gonna randomly sampling some values over here, and then we increase the revenue value, $8 to $10, for example, and more, little bit more and more. And then we can increase this one smaller, more and more. And then right after that, we can take the max min or min max or any kinds of variances here. So we may have min max or max min. We can use both of them. So when we are using min max or max min, we can guarantee the monotonically. So it means that we can increase the value more and more. We are not increasing the values. Okay, that's the main point here. So we have to think why we are using monotonic network. So here we want to this value more and more. We want to increase this value more and more. We do not want to. The auctioneer does not want to get $8 only. Auctioneer want to get the value as much as possible. That's why by using monotonic network, we are increasing the value more and more. In order to do some random sampling here, we are using these kinds of operations, okay? And then when we are, in order to take one value, eventually, we have max min or min max, and we have some proof which says that when we are using min max or max min, we can guarantee monotonic property here. So this is a PyTorch code about that. So as I told you before, allocation network is finding the bidder which is bidding the maximum value. So he's gonna be a winner. That's why we are using softmax in order to get the maximum value here. Then we're gonna determine who is the winner. And then in the payment matrix, eventually we have to apply the inverse function. Before applying the inverse function, we want to get only positive values. That's why we are using ReLU function here. Okay. So lastly, we have inverse function because this is we know our payment equation. So in our payment equation, we have these kinds of inverse function. That's why we have this one as well. So this is the final result. So suppose that we have 5 biddings. So when you look at the bidder, you can see which one is the maximum. So this one is maximum. This is negative values. That's why we're gonna ignore these kinds of 3 sampling results. So we have to compare both of them. So this is winner, but the payment will be this one because we are using second price auction. That's why this is the result of the second price auction. But with the deep learning, this is for determining who will gonna be a winner. So this is the maximum value. That's why it also says that number 4 is our winner. But actual payment is that using deep learning, we can increase this value up to 0.4438. So if we are using first price auction, the auctioneer will get 0.4430, and if you are using second price auction, we only have 0.37. But when you are using deep learning solution, then this value is nearby this one. That's why auctioneer will take revenue optimal property. This is second round. This is another trial based on this neural network. So then we have 4 results here, and only this one is negative value. That's why we're gonna ignore this one. This is number 2. This is 2, 3. This is number 1, 2, 3, and 5. When you look at this value, this is the first value. This is second value. That's why when we are using conventional second price auction, this will gonna be a winner, and he will gonna pay this amount of money. But we have a huge gap between them, right? That's why in order to improve this kind of payment a lot, we are using deep learning. That's why our payment becomes 0.9514, which is very similar to this one. That's why we are saying that we are based on the second price auction. That's why we are truthful. But in addition to that, our revenue is nearby the first price auction's result. That's why we are revenue optimal as well. That's why we are designing optimal auction based on the deep learning framework. So here we want to see how this kind of mechanism is applied to distributed computing. So these kinds of 3 mobile users are doing some blockchain mining, but the functionality in each mobile device is not that high. That's why they want to borrow some resources from cloud side. That's why they want to do some bidding in order to get the resources from this cloud. So this is based on the bidding mechanism. Okay, that's why we have to do some payment in order to increase the benefits here, profits here, and we have this algorithm should be revenue optimal for increase the benefit in auctioneer or seller. That's why we have to use the optimal auction theory here. So this is multi-drone charging scheduling. Suppose that multiple drones are flying in the sky. They want to be charged because their lifetime is very short. So in that case, we have a charging penalty here. So they have to do the charging scheduling. So, but if someone is malicious, then this one will stay here forever and ever, and the other drones cannot be charged, they'll be dropped. That's why the charging mechanism should be truthful. That's why we have to use the second price auction. And then in order to increase the profit in this auction year or seller, we have to say that this algorithm should be revenue optimal. That's why we have to use the optimal auction through the deep learning computation. Okay, so this is talking about that. This one was published in a transaction breakthrough technology last year from my group. So let me make a summary here. So in this lecture, we just briefly understand what's the economic theory and distributed optimization. For this purpose, we studied about game theory, stable management, and auction briefly, and then we want to, among these given three, we studied more details about the auction theory. So in auction, if you are using second price auction, it is truthful. However, it's not revenue optimal. That's why under the assumption of the second price auction, we have to increase the revenue. So in order to increase the revenue, we are using deep learning solutions. That's why, based on the deep learning, we are designing truthful as well as revenue optimal auction. And then we briefly see what can be the applications for distributed computing based on these kinds of optimal auction. So we saw brief introduction to mobile blockchain mining, as well as we briefly understand multi-drone charging scheduling. And here you can see the papers about that. So here we are using multi-drone charging scheduling examples. Here you can see the auction-based resource allocation in local energy market in smart grid. Lastly, we have application to smart manufacturing systems. So when you look at the papers one by one, you can see a lot of variances or applications of truthful auction. So this is the end of the presentation today. If you have any kind of questions, please let me know. Thank you for your active participation, and thank you for listening to my presentation.